My name is Feiyang Zhu, and I'm very happy to present this topic, which is about innovative 40-volt e-fuels for intelligent and integrated protection for the future vehicles. So in today's webinar, there are several topics we would like to discuss. The first one, we will look at the past and the current electrical and the electronic architecture used in the car. Basically, where a 12 volt is used as a low voltage power distribution bus, together with a domain architecture to manage all the electronic units. And because of the need of the fault prevention and the safety mechanisms, so the mechanical fuels is widely used to prevent the fault. However, as the car will become as a need to enhance the user experience, we are calling for a safer and smarter and more efficient car system for the future. And this requires to rebuild the system in a more efficient and smarter way. So basically, each subtopics will be upgraded to meet this requirement. So basically, the low voltage power distribution bus will increase from 12 volt to 40 volt, and the architecture will shift it from domain architecture to the zonal architecture, and the mechanical fuels need to be replaced by the e-fuels. And with all this upgrade, and we believe it will help to make a more safer and smarter and more efficient car system in the future. And then I would like to present this MPS integrated 40-volt e-fuel solutions to help to meet this system requirement and make the whole system more reliable and more smarter and more efficient. And the last, there will be a Q&A sessions to answer all the questions. Okay, first let's look at the car in the today's car, and actually there are a lot of electronics, and it is an electronic wonderland. So all these electronics can, based on the function, can be categorized into 5 major categories. First is the ADAS, which is advanced driver assistance system. The second is digital cockpit, which includes infotainment and clusters. And the third one is electrification. And the fourth one is the body control, and the fifth one is lighting. So for example, in the ADAS system, a lot of camera and sensor are used to collect data for the surrounding environments. And also a central computing platform is required to process this data to assist to help assist in the driving. And in the digital cockpit, a lot of electronics are added to enhance the user experience compared with the old days, such as the digital mirrors, USB wireless charging, and head-up displays. And in the electrification, as we know, due to the battery power electrical vehicles, the traction inverters is required to power the traction motors, and the onboard charger is required to charge the car battery from the grid. So with all these new functions, a lot of electronic hardwares are added into the car, and all these electronic hardwares need to be powered safely. So how does the car handle such a complex electronic system? So in the past and most of the cars in today, this is managed by and controlled by the domain architecture. So in the domain architecture, all the electronics are grouped based on the function. For example, for the ADAS, a lot of cameras and sensors are used in the different locations of the car. It could be in the front and rear, and in the middle of the car, and all these electronic related to the ADAS functions will be controlled and managed by one domain control unit. This means that it will require pretty long and complex wiring harness for the communication. And the second, all these electronic units are powered by a centralized power distribution box. So this means that this also require pretty long and complex wiring harness for the power distribution. So all of this will result in a complex and long wire harness in the car. And because of this complexity and because the need to prevent any fault and make sure the car, all the electronics operate in a safe state, we need to have a mechanism to realize this goal, and this is how the mechanical fields come to play. And there are usually these mechanical fields are located in a centralized power distribution box, as shown here. And there are several key purposes of these mechanical fields. First, since there are a lot of wires in the car, and there's a limitation for the current that the wire can be handled before it heat up and melt the insulation, cause a damage. So these mechanical fields need to protect these wires from heating up and causing any fire or damage. And second, the purpose is to provide electron units from fault condition, such as a short circuit. So in this way, the electronic units can always be kept in a safe operation state. And thirdly, since there are a lot of electronic units in the car, and if any of them have a fault happens, these mechanical fields need to make sure they can isolate the fault, so it will cause any further damage to the other electronic units. And lastly, this mechanical field is also used as a diagnostic feature. So during the maintenance, it's easy to identify the problem and to fix the and help the diagnostics. And that's how that's how the car system works in the past and most nowadays. Now let's look at the future trend in a car. So in the future, most likely your car will become your second living room, and it's for sure more and more features and functions will be added in the car to enhance the user experience. And with all this, the power demand in the car will increase dramatically. So, for example, take the ADAS example. As the ADAS level evolves from L2 to L4, the power requirement for this system can be up to 800 watts. And for higher quality audio system, the power consumption can be easily go to 2 kilowatts. And also for the to enhance to charge your portable device, the wireless charging power is also pretty large, 300 watt. And for smarter and more powerful seat control module, the power level is also quite large, 200 watts. So if we add all these power consumption together, it can easily to exceed 4 kilowatts in the future. And this poses a big challenge for the 12-volt system because there's a maximum current limit for the wiring harness in the car due to the insulation and weight and cost constraints. So usually the wiring harness in the car cannot handle the current larger than 250 amps. And if the system still operates at a 12-volt system, that means the max power it can support is around 3 kilowatts, which cannot meet the future power requirement. So in order to solve this issue, we have to increase the voltage level from 12 volt to 40 volt for the power distribution bus. And in this way, with the same current level, we can increase the power level provided by the car by 4 times. And in this way, we can meet the power requirement in the future. And there are several benefits by doing so. So here give an example of a 600 watt load. And by increasing the voltage from 12 volt to 48 volt, the current going through the wire can be reduced by 1/4 compared to the 12 volt system. Therefore, a smaller wire can be used, and a smaller wire help to reduce the weight of the wire, which is around 80% reduction. And although the wire becomes thinner and the resistance becomes larger, however, the current going through the wire is reduced more. So based on the Ohm's law, the loss in the wire still see a significant decrease, which is around 50%, even using a smaller wire for the 40-volt system. So by increasing the voltage from 12 volt to 40 volt, it can achieve a smaller size and lighter weight, and as well as a smaller loss. So in the future, the 40 volt will be a new 12 volt for the power distribution bus in the car. And during this transition from 40 volt to from 12 volt to 40 volt, the heavy loads which require more large power consumption will be moved to the 40 volt bus first, as this will give the most benefit, such as the AC compressor, your power steering system, and braking system. And then later on, the smaller loads will also move to the 40 volt in the future. And so this is the first trend. The voltage, but the voltage level need to increase to meet the future power demand. The second trend is that the electronic and the electrical architecture will shift from domain architecture to the zonal architecture. So in the zonal architecture, all these electronics are grouped based on the location and not based on the function, which is different from domain architecture. And the benefit that it can reduce the communication delay and also the wire harness for the communication. And the second, this zonal control units, each one will serve as a local power hub for the electron units adjacent to this control unit. So this also helps to reduce the wire harness for the power distribution. And together with more electronic control and with a central computing platform, it also enables a software-defined vehicle where the function in the car can be easily upgraded through the air without changing the hardware platform, and just like your smartphone. And the third trend is that the mechanical fields will be replaced by the electronic fields, which is a semiconductor device. So there are several disadvantages for the mechanical fields. First, it has a slow response with a very high fault tolerance. This means when selecting the wire harness, you need to add a more margin on the considering worst case, and this will increase the cost and also the size of the wire. Second is this mechanical field is non-resettable. This means once it's damaged, it has to go through a maintenance to replace it. And this increases the labor cost, and also is not preferred to enhance the user experience. Third, it only serves as a fuse, traditional fuse, and to protect the wires. There's no additional protection features and no monitoring or diagnostic features. However, this is pretty critical for the future system to monitor the whole system health and make the car more safer and more smarter. And then lastly, this mechanical fuse is suitable for centralized power distribution, but it's not good for the decentralized power distribution. So by replacing this mechanical fuse with the electronic fuse, which is a semiconductor device, all these disadvantages can be overcome. First, it can achieve faster response with a tighter fault tolerance. So this further helps reduce the wire harness complexity and weight. Second, this semiconductor device is resettable. So this means the software enables the software to control the load condition and the status easily, and it also reduces the maintenance labor cost. Third, a lot of extra protection and monitor features can be added into the semiconductor device, so to make it more smarter and to help to monitor the fault condition and the health state. Lastly, this semiconductor device enable a decentralized power distribution, which that means it can increase the robotics in the car and provide extra redundancy for the power distribution. So with all this change, this is how does the 40-volt zonal control unit with e-fuse architecture looks like. So in the future, there will be the power distribution bus will be 40 volt, and as load will transit from 40 volt to 12 volt, from 12 volt to 40 volt. So a local DC-DC converter to convert from 40 volt to 12 volt is still required to power these 12 volt loads. And meanwhile, since we have both 40 volt loads and 12 volt loads in the car, so 80 volt e-fuse and 40 volt e-fuse are both required to protect these loads. And this system provides the benefits as we mentioned before. It can help save the wire harness and make increase the communication speed, and has vast protection and diagnostic features. And additional benefits is that this whole system is scalable. It's a scalable solution, and also it's easy to be upgraded. This means that as more loads will move from 12 volt to 40 volt, the power consumptions of this DC-DC converter can be easily changed, and as well as the power consumption for the 80 volt e-fuse and 40 volt e-fuse. So by tuning these components, the system can be easily upgraded without touching the whole architecture. And all of this will enable a software-defined vehicle, which means that it can achieve a safer, smarter, and more efficient car system. However, by changing from mechanical fuse to e-fuse, there are also some new challenges we need to face. First is that the mechanical fuse is based on the Joule-Hitting principle, and it has an I to T curve, I squared T curve. And since we will replace this mechanical fuse in the semiconductor, Then the first challenge is how to mimic this mechanical field's behavior in a semiconductor device. Secondly, for this mechanical field, there's no electronics, so there's no power consumption. However, when we change to the semiconductor device, it will consume some power consumption, and the low power consumption is a critical feature for the battery connected device to extend the battery life. And the third one is how to integrate all the protection and diagnostic feature in the device to help to monitor the system health and in a harsh automotive environment. And then lastly, as these e-fuels will be used for different applications, we need to provide a scalable and compact solutions with cost-effective options, so that the hardware engineer can easily change this device without big design change to reduce the design effort. So with all these challenges, next I would like to introduce the MPS 40 volt integrated e-fuels family, the MPQ 588X series family, to solve all these new challenges. So first, this is a smart MOSFET with a lot of protection and diagnostic features. And this is an 80 volt device. So this means that it can easily handle the low dump, which is usually 70 volt in the 40 volt system. Second, it has a low quiescent current mode mode. By entering this mode, the quiescent current is pretty low, which is 25 microamps, and this can help to extend the vehicle battery life. And more details will be discussed later. It also has a lot of protection features, such as the fuse-like overcurrent protection to mimic the mechanical fuse behavior. It also has the short circuit protection for the harsh environment. And it also has the open load detection, which is also critical for the battery connected device. And all these details, all these key features will be discussed later. And for this device family, we have a wide options for different RDS(on), range from 2.5 milliohms to 50 milliohms to accommodate for different applications. And most of them are pin-to-pin and also footprint compatible in a very small QFN package. So this can help the user to easily drop in the different device for different applications. Next, I would like to highlight several key features for this family device. So first is the MPS proprietary fuse-like overcurrent protection feature. First, it has a current limit threshold. So once the low current exceeds this limit, then this fuse-like overcurrent protection will be enabled. And this current limit can be hardware programmable by external resistance on the CS pin, which is R5 as shown here. And the larger resistance value will result in a smaller current limit, which means it will trigger this overcurrent protection or start this the starting point for this overcurrent protection will be earlier. And to realize this to mimic this mechanical field's behavior, so it means that as the low current increase, as the low current become larger, the turn-off time of this MOSFET will be smaller. So in this way, we can achieve the to mimic mechanical fields, and also with a controllable fuse time variance in the semiconductor device. And the internal mechanism to achieve this is like this. So basically, there will be a external capacitance on the fuse pin, and once the load current exceeds the limit, a current source will charge this external capacitance. And once this external capacitance reaches a threshold value, the same current will discharge this capacitance, and the internal counter will increase. And once the internal counter reach a limit, then this device will think this overcurrent protection is triggered and to shut down the device. So as the low current increase, the current source to charge its capacitance will also increase. And in this way, we can achieve this I squared T curve as shown on the left-hand side. And also, this also means that this fuse curve can be hardware programmable by this C1 capacitance. And this a larger capacitance will make the turn-off time larger. So in this way, the fuse curve can be easily hardware adjusted to meet the application requirement. So here's more details about these field-like protection features. So on the left-hand side is showing how the MOSFET turn-off time change with the low current. On the x-axis is the difference between low current and the current limit value. For example, if the current limit is 15 amps and this 0 means that the low current is 15 amps, and if this 10, that means the low current is 25 amps. And as you can see, by increase the fuse capacitance value, it will take a longer time to turn off the MOSFET with a given low current. So in this way, the fuse curve can be easily programmed for different application needs. And on the right-hand side is a test waveform. As you can see, as the low current exceeds the current limit of the overcurrent protection, the fuse, the capacitance on the fuse pin will start to charge and discharge. And the internal counter will also start to count the number. And once it reaches the limit, it will shut down the device, and also the fault pin will pull low to notify the system that overcurrent protection is triggered. The next feature I would like to highlight is this low quiescent current mode. So in this device, there is a dedicated external pin to help the system to control this device to enter a low IQ mode to reduce the power consumption to extend the battery life. And this can be realized by control the OLD pin and enable pin. So once enable pin is high and the OLD pin is toggled to high, this device will enter into the low IQ mode. And in low IQ mode, the main FET will be shut off and the second MOSFET will be turned on. And this is a small MOSFET to handle a small low current. And because it's a small FET, so it requires less power to drive this FET. It helps to reduce power consumption. And also most monitor and protection feature are disabled in this low IQ mode to further reduce the power consumption. And a next feature of this low IQ mode is that it can achieve automatically exit low IQ mode and transit to normal mode without the external system help. So this means that if there's some low condition change and the low current increase dramatically and exceeds the threshold value, this device will automatically exit the low IQ mode and enter the normal mode. At the same time, the fault pin will also pull low to notify the system to help for the diagnostics. So this is a detailed test waveform for this low IQ mode. First is the entry of the low IQ mode. So if the low current is small enough, which is around the 200 amps in this device, and once the user toggle the OLD pin, then this device will enter the low IQ mode, and you can see that this is a smooth transition and there's no spikes on the output voltage. And if the low current, however, increase dramatically from a small current to a large current, this device will detect the drain to source voltage, and if it exceeds the threshold, it will automatically exit low IQ mode and turn on the main FET. And as you can see, when it exits low IQ mode, the fault pin will pull low to notify the system. And in order to retoggle this, reset this fault pin, the OLD pin need to be retoggled. And the third features I would like to highlight is this open load detection feature. So this open load condition is a fault condition that can be usually caused by two scenarios in the car. First is that since a lot of wires used, and if the wire connection is not stable, this can cause a high impedance seen from the output pin of this device. Second, since there's a battery in the car, and it's possible that this battery voltage will be short directly to the output pin of this device. So because of these two conditions, the open load detection feature is critical in the automotive application. And in order to achieve this detection mechanisms, we also have a dedicated outside external pin to enter this open load detection mode. And this is also controlled by the enable pin and OLD pin. So once enable is off, which means that device is in the off state, and if the OLD pin is pulled high, this device will enter the open load detection mode. And in the open load detection mode, a current will be sourced from this output pin. And because there is a high impedance on the output side, so the output voltage will rise up. And once it triggers threshold value, then this device will detect as an open load fault, and the fault pin will also pull low to notify the system. So on the right-hand side is the test waveform. As mentioned, when the OLD pin is pulled high, it will enter the open load detection mode, and the output voltage will start to rise because there will be a constant current source to charge this high impedance. And once it's triggered, exceeds the threshold value, this fault pin will pull low to notify the system to help for the diagnostics. So with all these key features, it can help solve the new challenge by changing from mechanical fields to e-fields. And also this help to provide more diagnostic and monitor features to make the system more smart and safer. And lastly, I would like to show the comparison between the legacy approach and MPS integrated 40-volt e-fuel solutions. So in the legacy approach, usually a separate controller and MOSFET will be used. And also, external current shunt resistance is required for the current sense and current-related protection feature. And the external temperature sense is required for the temperature monitoring and protection. However, by integrating all these features in one semiconductor devices, the BOM cost and also the footprint can be reduced a lot by using MPS integrated solutions as shown here. So this integration provides massive benefits. It also makes the system more reliable and can help achieve a safer and more smarter car system in the future. Lastly, I would like to summarize these key takeaways in this webinar. So first, we talk about the limitation of the conventional car system, which the 12-volt is used as a power distribution low voltage bus, and the domain architecture is used to control the all electronic units, and the mechanical fields is used to prevent the fault condition. However, all of these aspects need to be upgraded to achieve a safer and smarter, more efficient car system in the future. So that's why we need to increase this 12-volt from 40-volt for the power distribution, and change from domain architecture to the zonal architecture, and the shift from mechanical fields to e-fields. And by doing so, there are several new challenges where we need to solve for the e-fuels, and this MPS integrated 40-volt e-fuel solutions can help the system to achieve these goals. So it has a fast response time and tight fault tolerance, and it has a vast protection and diagnostic features, such as this open load detection and the low IQ mode, and the current sense and temperature sense, and all these are critical for these automotive applications. And finally, this is an integrated solutions, so it can dramatically reduce the BOM cost and with a compact size.